In the last lecture, we talked about a problem called Simon's problem. In some sense, among the minor algorithm, that was one of the significant development in quantum computing. In the next couple of lectures, this one and the next couple of lectures, I will be discussing one of the more significant algorithms, which along with another algorithm that I will be talking about, have been so far the most significant results of quantum computing. The algorithm that we talk about today is due to Grover. Actually, he is an Indian, Love Grover. The algorithm is a database search. It is popularly known as Grover's search algorithm. The problem is something like this, that suppose I have an unstructured database. The unstructured database is basically a database in which there is no particular order. If you take a telephone directory, for example, the old classical telephone directory, that was a structured database, because you could go through the names in an alphabetical order and then find out the person that you want, their telephone number. But suppose I give you the same telephone directory and ask you to find out the name corresponding to a person whose telephone number has been given. Now, and you do it by a classical search, that is obviously a very tall order. Typically, if I have a database of capital N, which is our short notation for 2 to the power small n, n is the number of qubits, then I would require order n searches. And in a probabilistic way, I can say my search will be successful with approximately n by 2 searches. So this is the classical algorithm, and this for large n, it becomes a hard problem. Now, I have already discussed earlier what is a hard problem, that it cannot be done in a polynomial time, but this is a type of problem where given a solution, checking whether the criterion for the search is satisfied is an easy problem. That is, if I have a certain characteristic given, then I can always put the solution back into my statement of the problem and find out, yes, this is indeed a solution. The checking a solution becomes easy, but finding that becomes hard. Now, Grover's search algorithm actually accelerates this search from order n to order square root of n. That is a quadratically speeded up search, and this is a reasonable acceleration of the number of searches that we need. So, as we had already said, that let capital N equal to 2 to the power n, which is our n qubit data. Now, I need an oracle which will calculate a function, and this function is what I would call as a needle in the haystack function. So, the needle in the haystack function this is defined over set of integers k. So, let us call it integers k. So, k is a number which runs from 0 to 2 to the power n minus 1. Remember, 2 to the power n I will frequently be writing as equal to capital N, such that the oracle can calculate a function f. Value of f of k is equal to 0 for all k not equal to a particular value w. Now, if k happens to be equal to w, then the function evaluates to 1. Our problem is that given a large number of k, which is capital N number of k's, an oracle which can calculate f of k at every stage how do I find out what is this string W for which f of W happens to be equal to 1 while all others evaluate to 0. Grover's oracle schematically is as written here, that oracle calculates f, I have put argument W of x, that is equal to 0 if x is not equal to W and is equal to 1 if x is equal to W. So, as again this is something which we will be repeating several times because this is the crux of many things. I have an input x, I have a target y, and the function is calculated by the oracle. The input remains unchanged, but the target will now store y addition modulo 2 with this function that we have calculated. Now, suppose my y is put to be equal to 0 minus 1 by 2. So, let us look at if y is equal to 0 minus 1 by root 2. Remember, my target is y plus fx, let me call it fw of x, just to keep on reminding ourselves that there is a special w there. Then, if y is equal to 0, the output is just f of w. If y is equal to 1, this is just the complement of w. So, in other words, I can write the target as equal to minus 1 to the power fw of x, which is, this is my including my first register, with 0 minus 1 by root 2. Now remember, my fw of x evaluates to either 0 or 1. Now when it is 0, this is 1. So therefore, I of course expect what is, if fw of x evaluates to 0, then the content is simply y, which is equal to 0 minus 1 by root 2. On the other hand, if fw of x evaluates to 1 when my string happens to be equal to w, then it is y plus 1, which is nothing but 1 minus 0 by square root of 2, which is what I have indicated. So, since this is the one which has an x dependence, I can put it along with the first register and write it in this fashion. So therefore, notice that my second register is unchanged. But my first register will have its sign flipped if fw of x is equal to 1. In other words, for the given string, if fw of x equal to 1, the sign of the first register will be flipped. So let us look at what type of unitary operator will do it. So I define a unitary operator corresponding to this w, and I define this by I minus 2 times get w bra w. So look at how we are going to do this. Now when this acts on the state w, then I get w minus 2 times w, which is minus w. So if we will take a linear combination of the computational basis as all our inputs, and there are capital N of them. Out of that, there is a specific w, and all these basis states are orthogonal to each other. So if this uw, which is acting on a state w, which by definition is orthogonal to all other members of the states there, then I get minus w. So this uniform linear combination, let me, instead of confusing with x, let my x be the n qubit basis. Let me call it a standard state with which I start. So this standard state, as we have written several times, 1 over square root of n sum over x equal to 0 to n minus 1 x, where x is a collection of all the states in the computational basis. By definition then, since W is a member of this collection, then my scalar product of W with S, remember in this sum, it's a uniform linear combination. So as a result, each one of the members has equal weight, and this scalar product is then 1 over square root of n. Now Grover defined a second operator called reflection operator. Grover defines a reflection operator. We will see why it is so named. The reflection operator US is 2SS minus I. Remember the other operator which we had defined earlier was UW equal to I minus, there is a order in which these have to be written. Why is this a reflection operator? Suppose I let it act on an arbitrary state psi, any state. Now, any state psi I can resolve into a component along the standard state S and a component perpendicular to it. Now notice that if I write this psi parallel plus psi perpendicular, this is parallel and perpendicular to the state S, then acting on this, the component parallel to S will be unchanged. But the sign of the state perpendicular to S, see if a perpendicular to S is there, then this term will give me 0 because this is parallel to S, perpendicular to S is the scalar product is 0, and the component perpendicular, this is an important point to note, component perpendicular to S will be flipped, will change sign. Grover's operator, which we will call simply as a Grover operator, Grover rotation operator also it is called, RG is defined as UW followed by US. Now what we will do next is to look at a geometrical interpretation of what this means. So let us collect our thoughts again. We have UW equal to I minus 2 WW and US is 2SS minus I and UG RG is equal to US UW in that order. So let us look at this for the geometrical interpretation of what does the Grover operator do. So what I am going to do here is the following, that I have taken an arbitrary state psi here, and this arbitrary state is, let us say, making some angle phi with the W. Now look at the colored things that are there. The W is a member here, so I have got a W and W perpendicular. This is the representation of a vector. Now S is given by this red line, and perpendicular to that is your S perpendicular direction. And there is an arbitrary angle between S and the W perpendicular. Now supposing I just talk about an arbitrary vector psi. Now if I have an arbitrary vector psi which is making an angle of phi with the W, so what does this do? First thing that I do, as I told you, I resolve the arbitrary state along W and perpendicular to W. Now when I apply RW to it, it will flip the sign of the component parallel to my W. So let us look at what it takes me to. So this picture, if you look at it, I have my psi here. So the component of psi parallel and perpendicular to W, you can mentally resolve this. This will be parallel to W and this much will be perpendicular to W. When I apply the UW operator on this, we have seen that the component parallel to W will be flipped. So therefore, this just turns back on this side. This is psi 1. So this angle phi must be the same as that angle phi. So that psi becomes psi 1 when you apply EW. My second job will be to apply US to it. Now remember what is US? My US was 2SS minus I. So what I do is, I resolve psi 1 now into a component parallel to S, which is not shown here. The component perpendicular to S is being shown there. And of course, you can immediately see that if I had extended this red line, then I will have this much or this much, which is parallel to S. Now what the US operator will do will be to flip the component perpendicular to S. So therefore, this one will now come to psi 2. This one will come to psi 2, and so therefore, this is S perpendicular component has been changed. And these are fairly straightforward angles. This angle must be equal to that angle because that's the way I have reflected it. And if this angle happens to be chi, then this is chi. Now look at the geometry here. This angle between this line and that line here. So this must be equal to phi plus chi, which is here. This is should be read as theta, both of them, like 0 in the picture. The slide says theta. And so therefore, this is what happens. Now, you can immediately check that by a trivial geometry, that the angle by which you have to rotate psi in order to get to psi 2 is twice the original angle theta. This is theta, and in order to come from this psi to this psi 2, you have to rotate it by twice. This is phi plus chi is theta, so there is a phi plus chi here, there is a phi plus chi there, so that is 2 theta. Now this is what would happen to an arbitrary psi. Now what you do is, now that you have realized that what Grover operator does is to, acting on a state, any state, rotates it by 2 theta, where theta was defined by us earlier. Then I can apply it on the standard state S itself. Instead of arbitrary state, take an application of what is it doing to a standard state. An example will sort of explain to you what I am doing. Suppose I take just 4 elements. Of course, you would say 4 elements is so trivial that I could do it classically, but that's not the point. Point is that if you have 4 elements, in principle to find a match, you need on an average, 3 will definitely make sure which is it, but on the other hand, let's say on an average between 2 to 3 or 1 to 3 you will take. But then in this case, the angle between S and W is 60 degrees. Now single rotation, remember theta was 30 degrees in that case, because 1 over square root of 4, that is 1 by 2 sine inverse is 30 degrees. So if I now rotate it by 2 theta, since theta is 30 degree, 2 theta is 60 degrees, which will immediately align S with W. In other words, a single rotation, Grover rotation, is good enough to align the standard state S along a marked state. Now you would say, now this is incidentally not always true. Look at what happens if I have n is equal to 8. So we have seen that in principle I would need classically about half of the searches. In this case, my sine theta is 1 over square root of 8. And if you calculate using a calculator, you will find theta happens to be 20.7 degrees, approximately 21 degrees. Now, if theta is 21 degrees, the angle between S and W here is 69 degrees. And a single rotation will rotate it by 21 degrees to 42 degrees approximately. It's actually 20.7, so it is 41.4, but doesn't matter. I'm just giving you approximate ideas. So the first rotation will make this angle 17 degrees. In other words, it has decreased a bit. But if you do a second rotation to make it worse. So therefore the idea is I must know a priori how many rotations I want. If your n increases, then the steps of every rotation is small. And then I can control it much better. And I can then use much less number of rotations in order to get the S. If it is not exactly aligned, closely aligned with the marked state. I will continue with the Grover problem for the next as well as the following lectures. But let me summarize for today. What is it that we have done? What we have done is to start with an unstructured database of n number of elements. Corresponding to each one of the elements, there is a member of my basis states, n cubic basis state. I have an oracle which calculates the function corresponding to every member of this computational basis. There is a needle in the haystack function which the oracle calculates, which evaluates to 1 if the input string happens to be the marked string W and is equal to 0 if it is not the marked string. Having done that, we gave a geometrical interpretation to the Grover rotation operator. So what we found is this, that starting with a uniform linear combination of basis state and a given marked state having that property, application of Grover rotation would make my standard state come closer and closer to the marked state. And this, the number of attempts that you will require, as we will see in the next lecture, is of the order square root of n instead of order n, which we require for a classical search.